Graphs are everywhere. We use them for maps, social networks, and even the internet. In computer science, we use graphs to represent connections between things. Think of a graph like a network of dots or nodes connected by lines or edges. Graph traversal is like taking a journey through this network. It's the process of visiting every node in the graph systematically. Why is this important? Because it lets us solve all sorts of interesting problems. Imagine you want to find the shortest path between two cities on a map, or maybe you need to find all the friends of a friend on social media. Graph traversal algorithms like breadth-first search or BFS and depth-first search or DFS come to the rescue. These algorithms provide a structured way to explore graphs and extract meaningful information. Let's dive in and learn more about these powerful techniques. Imagine you're exploring a maze. You start at the entrance and systematically explore all the paths branching out from your starting point before moving further. That's the essence of breadth-first search, or BFS. BFS is a graph traversal algorithm that explores a graph level by level. It starts at a designated root node and visits all the node's immediate neighbors. Then, for each of those neighbors, it visits their unvisited neighbors, and so on. To keep track of the nodes to visit, BFS uses a queue. Think of a queue like a line at a ticket counter. First in, first out, we add the root node to the queue. Then we repeatedly dequeue a node, visit it, and enqueue all its unvisited neighbors until the queue is empty. This level-by-level exploration makes BFS particularly useful for finding the shortest path between two nodes in a graph, especially in unweighted graphs where all edges have the same cost. Let's say you want to find the shortest path from your house to your friend's house in a city. You can represent the city as a graph with street intersections as nodes and streets as edges. BFS can help you find your way. Starting at your house, the root node, BFS would explore all the intersections directly connected to your house. Then it would explore the intersections connected to those intersections, and so on, until it reaches your friend's house. Because BFS explores level by level, it guarantees that the first time it encounters your friend's house, it will have found the shortest path. This is incredibly useful for navigation apps, network routing protocols, and various other applications. Unlike BFS, which explores level by level, depth-first search, or DFS, dives deep into each branch before backtracking. Imagine you're exploring a maze. But this time you pick a path and keep following it as far as you can before trying other paths. DFS starts at the root node and explores as far as possible along each branch before backtracking. It uses a stack to keep track of the nodes visited. When it reaches a dead end, it backtracks to the last node with unexplored neighbors. This deep exploration makes DFS suitable for tasks like detecting cycles in a graph, topological sorting, and finding strongly connected components. Section 5, DFS in action, mapping out a maze. Imagine you're designing a computer program to solve a maze. DFS can be your trusty guide. Represent the maze as a graph, with each cell as a node and walls as barriers between nodes. Starting at the entrance, DFS dives deep into the maze, exploring each path as far as possible. If it hits a dead end or the maze's edge, it backtracks to the last intersection and explores an alternative path. This process continues until the program finds the exit. DFS systematically explores all possible paths, ensuring that the program eventually finds a solution if one exists. This makes DFS a powerful tool for solving puzzles, mapping out complex structures, and more. Section 6, BFS versus DFS, choosing the right tool. Both BFS and DFS are powerful graph traversal algorithms, but they have different strengths and weaknesses. Choosing the right one depends on the specific problem you're trying to solve. BFS is like exploring a maze systematically, level by level. It's great for finding the shortest path, especially in unweighted graphs. DFS, on the other hand, is like diving deep into a maze, exploring each branch before backtracking. It's useful for tasks like cycle detection and topological sorting. Here's a table summarizing their key differences. Feature BFS versus DFS exploration order, level by level versus depth-first data structure, queue versus stack or recursion, shortest path guaranteed in unweighted graphs versus not guaranteed, cycle detection not ideal versus well-suited, memory usage can be higher for dense graphs versus Generally, lower understanding these differences will help you choose the most appropriate algorithm for your specific needs. Section 7. Applications of BFS from social networks to web crawlers. BFS's ability to find the shortest path makes it incredibly useful in various real-world applications. Let's explore a few examples. Social networks. Social media platforms use BFS to suggest friends of friends. By treating users as nodes and connections as edges, BFS can efficiently identify users who are 1 or 2 degrees of separation away. Web crawlers. Search engines use web crawlers to index web pages. BFS helps these crawlers systematically explore web pages by following links, ensuring that they discover and index pages in a structured manner. Network routing protocols. Use BFS to find the shortest path between routers in a network. This ensures that data packets travel efficiently across the internet. Garbage collection. Some garbage collection algorithms use BFS to identify reachable objects in memory. By starting at root objects and following references, BFS can determine which objects are no longer in use and can be safely deleted. These are just a few examples of how BFS is used in practice. Its versatility and efficiency make it an essential tool in computer science and beyond. Section 8. Applications of DFS, navigating mazes and solving puzzles. DFS's deep exploration capabilities make it well suited for maze solving. DFS can systematically explore a maze to find a path from the entrance to the exit. This technique is used in many maze-solving algorithms and games. Many puzzles, such as Sudoku and crosswords, can be solved using DFS. DFS explores different possibilities until it finds a solution. These applications highlight DFS's ability to delve into complex structures and solve problems. Section 9. BFS and DFS implementations, a practical perspective. Implementing BFS and DFS is straightforward in most programming languages. Use a queue for BFS, stack or recursion for DFS, and track visited nodes to avoid infinite loops. Here's a simple Python implementation of BFS. Import default dec, define BFS with graph and start_node. The graph is a dictionary with nodes as keys and adjacent nodes as values. The function returns nodes in the order they were visited. Define a graph, set start_node to A, call BFS, and print the traversal order. Section 10. Beyond the basics, advanced graph algorithms and techniques. BFS and DFS are fundamental graph traversal algorithms that form the basis for many other graph algorithms and techniques. Some advanced concepts include Dijkstra's algorithm, which is an extension of BFS that finds the shortest path in weighted graphs where edges have different costs. Next up is A** search, a heuristic search algorithm that uses heuristics to guide the search towards the goal node, making it more efficient than BFS in many cases. Then we have the Bellman-Ford algorithm, an algorithm for finding the shortest paths in a weighted graph with both positive and negative edge weights. And lastly, the Floyd-Warshall algorithm, a dynamic programming algorithm that finds the shortest paths between all pairs of vertices in a weighted graph. These advanced algorithms build upon the principles of BFS and DFS to solve more complex graph problems efficiently. Section 11. Conclusion: the power of graph traversal. Graph traversal algorithms, particularly BFS and DFS, are essential tools in computer science and beyond. They provide a structured way to explore graphs, extract meaningful information, and solve various real-world problems. BFS's level-by-level exploration makes it ideal for finding the shortest path, while DFS's deep exploration capabilities are well suited for tasks like cycle detection and topological sorting. Understanding the strengths and weaknesses of each algorithm allows you to choose the right tool for the job. From social networks to web crawlers, from maze solving to puzzle solving, from network routing to garbage collection, BFS and DFS play a crucial role in shaping the technology we use every day. Mastering these algorithms empowers you to tackle a wide range of problems and contribute to the ever-evolving world of computer science.